So today we're going to begin with a fun game of Jenga. Now, can anybody tell me the way the game is played? Andrea?
You take turns removing a block and you hope it doesn't fall.
Right, so the winner is the one who doesn't knock over the block. So what if I try to take from the top here? Can I do that?
No, that's against the rules. You have to take it from the middle.
Oh, okay. We'll try to take one from the middle.
Alright. I got one.
Then I'll go. Oh no! I guess I lose. So how did the blocks fall over? Can anybody tell me that?
Mary Kay, move the table.
Mary Kay, move the
Cheater.
table. Cheaters. So the table moved, and it shook the blocks, and as you saw, the blocks fell. So let's think big. How can we relate what happened here between the little table that the blocks are sitting on and the blocks themselves to larger real-life objects like buildings or bridges?
Earthquakes.
Earthquakes, right. So, what have you been learning about that might have caused the blocks to fall over?
Seismic forces.
Right, forces. And as we know, earthquakes are caused by seismic forces. So, what causes these seismic forces? Does anybody know?
The plates.
So the moving of the plates in the Earth's crust is what causes these seismic forces. So, what causes these seismic forces?
The movement of the plates.
The movement of the plates, right. And so we call this the movement in the Earth's crust is called plate tectonics. Now, what if we had a bridge here on the table before it collapsed? What would happen to the bridge?
It would wobble.
Right, it would wobble. It would start to move backwards and forwards, side to side. Right? So, what causes these bridges to fall? So their structure is already messed up because of all the shaking. But what actually causes them to fall? What's pulling them down?
Gravity.
Gravity, right. So we don't want our bridge to collapse with cars on it, right?
No.
So how can we design a bridge that can withstand something like the earthquakes that we feel?
Make it stronger.
Right, we can make the bridges stronger. And that brings us to our question of the day, which is, which characteristics help bridges be resistant? What would happen if we put Jell-O on our table? Now that we have our Jell-O set up, let's shake the table to simulate another earthquake and see what happens with the Jell-O. Okay, now can anybody tell me what happens to the Jell-O? How does the Jell-O react?
It moves.
Right, it moves, it wiggles. How does it react when compared to the Jenga blocks?
It doesn't fall.
Right. So here we see during our earthquake, the Jell-O isn't falling. It's flexible, it's moving with the motion of the earthquake. How does the structure differ from the Jenga blocks?
It holds together. It's one piece.
It's not hard.
One piece, and it's not hard. This Jell-O is flexible. Like I said earlier, it can move with the earthquake. So ideally, we want structures that are more flexible.
Earlier we discussed that movement in the Earth's crust is called plate tectonics. But how does that movement happen? What causes it?
Convection.
Very good. And what is convection?
When heat rises and then it cools and the air goes down.
Right, it's the constant moving of heat and cold air in the Earth's crust. Very good. I want everybody to rub their hands together, just like this. And I want you to tell me where the forces are on my hands right now.
Gravity.
Gravity, so gravity goes down.
Yes.
So what's going up?
Normal force.
Normal force. So we have one going down and we have one going up. Very good. Where else are the forces happening?
Between our hands.
Friction, okay, and what direction are they happening?
Opposite and forward simultaneously.
Side to side.
Very good, and which of Newton's laws explains that?
Third.
Newton's third law of motion, which states that if for any action there is an equal but opposite reaction, you can stop by rubbing your hands together. Thank you. Now we're going to look at some examples of bridges that already exist today. Looking at these examples, which one do you think is most like the Jello?
The one on the right top corner.
This one?
Yeah.
Very good. And which one do you think is most like our Jenga block tower?
The one on the bottom.
This one?
First. The ladder.
Maybe the ladder?
First one.
Okay. Those are good observations. Which one would you be the most afraid to walk on?
The second one.
This one up top? Which one would you feel the most comfortable walking across?
The middle
The
one.
third.
This one in the middle?
Yes.
Definitely looks to be the most safe. I agree. What does this bridge look like? Have you already seen a bridge like it before?
The Brooklyn Bridge.
Brooklyn Bridge? Okay.
The Golden Gate.
Okay. Interesting. What about the one here in Austin? Just look like maybe the one here in Austin structurally? Going over
Congress.
Congress. Very good. Those are good observations. So I want you to keep these bridges in mind as we do our explore today. You're going to be building your own bridge out of toothpicks and marshmallows. But before we get started on our activity, I think it's important, because we're such good scientists, that we should come up with a hypothesis about how to build the best bridge possible. What is a hypothesis?
A prediction that can be tested.
Prediction that can be tested. Very good.
An educated guess.
Educated guess. Those are both great answers. So before we begin, I'm going to pass out a worksheet. And on it, you're going to write your hypothesis on how you're going to build your bridge. So now that everybody has a good hypothesis written down, let's take a look at the rest of our worksheet. It says, list 2 important things that your bridge will need. What are 2 important things you think your bridge is going to need?
Flexibility.
Okay, so write that in number 1, flexibility. Very good. And what about number 2?
Support.
Support. I like it. Okay. So for your bridge, each person is going to get 20 toothpicks and 40 marshmallows. Nobody is going to get any more or any less. It's also important to note that these are scientific materials, and so they're going to be used for scientific purposes only. You're not going to touch your partner with them. You're not going to poke anybody with them. They're scientific tools. And before we pass out the materials, I want everybody to draw an example of what their bridge might look like in the squares below. I'll give you 1 minute to talk with your partner and make a rough drawing. Great. Now that everybody's drawn their bridge and everything looks good, I think it's time to pass out the materials. We're going to pass them out, and you'll each have 20 minutes to build your bridge. And as soon as everybody's done building their bridge, we're going to test it on our shape table, just like we did with our Jenga tower and our Jello. And we're going to see which one stands up longer.
So, would anybody raise their hand to tell me if their bridge stayed up? Okay, Andrea, your bridge stayed up. Can you tell me why?
It was very flexible. Well, not too flexible, but like kind of flexible.
Exactly. It was the perfect combination of the flexibility we saw in the Jello, not too rigid, and the strength that we saw with the Jenga blocks. So, can anybody tell me what shapes we used? That you might have used to make your bridges?
I used a triangle.
Right, we used some triangles, anything else?
Squares, rectangles.
Squares. We use triangles and squares. That these shapes help to stabilize the bridge more. You'll find that the strongest shape to stabilize the bridge is generally triangles. So many bridges have extra beams to help support the weight. And these are called trusses. Now the trusses, as you can see by the definition, are extra beams positioned at angles throughout the structure to add support. And you also might have seen these in the large beams cross-sectioning in between our smaller beams. Those are the trusses that you see. Now in the real world, we can think of our model here, the table that we use to shape the Jenga blocks and the Jello, as the ground that we stand upon. And the objects were the bridges or the buildings that we see day to day. And the movement of the table was to simulate the seismic forces of the shifting plate tectonics. So in the real world, the shaker table is the ground that we stand upon, and the objects that we put on it, like the Jello and the Jenga blocks, are supposed to simulate the buildings. Now, the shaking of the table simulates the seismic forces of the shifting plates that apply a force to the object in order to get it to move. Now, can anybody tell me what is the force that an earthquake causes?
Seismic.
Seismic, correct. Seismic forces are applied to the bridge by the earthquake. The table is the ground, and the movement is the shaking of the table. The movement is the seismic forces that get applied. So we use a certain tool called a seismograph to record data from the earthquake based on the strength of these seismic waves. Here is your very basic definition. The seismograph is a machine that measures the strength of an earthquake. Now, we also use a Richter scale to give a number to the earthquake. Each higher number is 10 times stronger than the previous. The numbers that you see there are each 10 times stronger than the last. So here's a helpful model. And you'll see that the 2 is actually 10 times stronger than the 1. Now the Richter scale is used to tell us how powerful each earthquake is. So we measure these numbers and we compare them. Now, our bridges did well, and they give us an idea about what could happen in real-life situations. But what are some problems that we might run into if we try to use this on a larger scale? Or if we try to use this as an example of the way we should build our bridges?
It wouldn't be as accurate.
Right, it wouldn't be as accurate. Can anybody come up with any reasons as to why it wouldn't be as accurate?
Because cars are heavier than you think.
Cars are heavier than you think. Anything else?
There's a lot of factors involved.
There's a lot of factors. There's plenty of variables, like the cars being heavier than we think, the way the elements are going to interact in that specific environment with the tools that we use to make the bridge. And that's basically why it becomes much harder to test these things, but this is a good model for teaching purposes. So we talked a lot about different types of bridges today, and these different designs allow professionals to build bridges in different places.
Today we talked a lot about bridges, their structure, their use. That's because they're really important to our everyday lives. Let's take a look at the history of a bridge. So it started out with being built by nature. Where have you seen bridges built by nature before?
In the woods.
The woods, maybe a tree fell, like the one in the picture. Where else? Maybe in a park, when you were at the park.
Yeah.
Maybe. Okay, let's take a look at some others. These are some of the first man-made bridges built by the Romans. They used semicircles instead of triangles, but they didn't do that. These were actually used to transport water originally. They're called aquifers. And these were very important to having running water for the first time in civilization. We have Darby's built the very first bridge made out of iron. Why do you think that's a really important discovery? Why is it important that this bridge was made out of iron and steel?
Because it could support heavier things.
Very good. So this was actually built around the time that the first automobile was discovered, and they needed a way for the automobiles to be driven across. There's streams and other pathways. And here's a bridge. It's a little more modern. This one's in San Francisco. This is the Golden Gate Bridge. We also have the Tower Bridge of London, the Sydney Harbour Bridge in Australia. These bridges are a little more intricate and have a little more thought put into them, so they're more visually appealing than the ones that we've seen in previous. This is a broken bridge based on an 8.0 earthquake in Japan off the Richter scale we talked about earlier. Let's look at another one. This one is also in Japan. Oh, it's really bad. Why do you think these bridges were not able to withstand the earthquakes? Just based on your observations.
They weren't strong enough or flexible.
Right, or any combination of those. So it's really important that we understand what helps our bridges stay strong in incidents like earthquakes so that everybody can be safe and make it home. So that is the end of our evaluation. Let's get out a pencil and let's get ready for the show what you know.